Okay, so we just looked at the concept of moment inertia. Okay, so this was the two sticks I asked you to play around with, or you could actually make or watch a couple videos. Okay, all right, so we wrote this, okay, moment of inertia, okay, sum of mr squared. That's for point particles, right? So it literally means you go to each mass, you multiply by the distance from the axis of rotation out to the mass squared, and so on, okay? Now, for a continuous mass distribution, all right, we're going to make the connection that instead of point particles, I have some odd shape, and I want to rotate it about that axis, okay? So this was for point particles, okay? That was for point particles. So we're going to make the connection between the discrete world of point particles to a continuous mass distribution like this weird-looking potato, okay? So instead of summing over each point mass, I'm integrating over the mass distribution, okay? Instead of r, okay, instead of r being the distance out to each point mass, okay, now r is the distance out to the mass element dm, okay? So we're going from the discrete world to the continuous world. So that's how I find the moment inertia of a continuous object about some axis of rotation. I think I called it axis A, okay? So it has the same form as a form of mass times the distance squared, mass times the distance squared, okay? But it looks a little different because of the order. Here is something over mr squared. Here integrating r squared over the mass over m, okay? The mass element is dm. So let's see how you actually use this. Okay, so I want to find okay, so again, let me go back, all right? Okay, we had moment inertia, the center of mass. I'm summing over mr squared. Okay, there's my stick, there's my point masses, okay? Don't get this confused with center of mass. Okay, if I want to find the center of mass, okay, that's a location. I go to each location, multiply by its mass, but that doesn't give me location. I have to divide by mass so that the units cancel, okay? So don't confuse that with that, okay? They look totally different, all right? And they mean two totally different things. Okay, all right, so I want to find the moment of inertia about the center of mass for a thin homogeneous rod, mass m, length L. So let's say a meter stick, okay? And by thin, I mean we're ignoring that dimension, okay? So it's thin, all right? So it's like a wire, all right? Okay, so I want to find the moment inertia about the center of mass, okay? That's my axis. Okay, so I'm going to rotate it about that axis. So this would be like the example of you held your pencil here, and you rotated the pencil about that axis, almost like you do like the rubber pencil type thing, okay? Well, r is the distance out to the mass element dm. Okay, so I'm doing this in one dimension, okay? So in one dimension, I have an x-axis, so x is the distance out to my mass element dm. There's my mass element. Okay, so instead of a point mass, it's a mass element, and x is the distance from the axis rotation out to that mass element. Okay, so the problem is my my integrand is in x, my variable of integration is m, so I can't integrate that. So I have to change the variable of integration or change the integrand. Okay, so what we do is we introduce something called a linear mass density. Okay, so lambda is mass per unit length. Okay, so a lot of books like to use lambda for linear mass density. They use a rho for volume density. Okay, so mass per unit length. So lambda is mass per length, and my length dimension is the variable x. Okay, so multiply both sides by x, so m is lambda x. Okay, and this is going to remind you of when you first started doing u substitutions in Calc 1. So I'm going to take a differential of both sides of this. So take a differential of both sides. So dm is lambda dx. So right here where I have dm, okay, right there I have dm, I'm going to put in, right here where I have dm, I'm putting in lambda dx. Okay, and look at my limits of integration. Okay, so this stick has mass m length L, so that's L over 2. This is x equals 0. That coordinate is minus L over 2. So I'm integrating along the stick from minus L over 2 to L over 2 of x squared dm, but dm is lambda dx, Okay, so it's a homogeneous, so it's a uniform stick, so lambda comes outside. Okay, so now I'm integrating x squared from there to there. Okay, now if I look at the next step, all of a sudden there's a 2 here, and I'm integrating from 0 to L. So what I did is, hopefully you saw that in Calc 1 or maybe in Calc 2, that if I have a function, okay, so my function is x squared. Okay, so it's parabolic. Right? So this is an even function. So if I integrated this from there to there, okay, if I integrate from there to there, it's an even function, meaning if I put in a minus, it's squared, I get the same function out, okay, that's the same as integrating 2 times just that side. Okay, so I'm using the evenness of the function. Okay, so that's where the 2 came from, and integrating from 0 to L over 2. Okay, and I don't have to do that, just makes the integration easier. There's my 2 lambda, okay, because now my lower limit's 0. So x squared integrates to x cubed over 3, and I put it in my upper limit minus my lower limit, which is 0. So just be careful. There's my upper limit. Okay, so there's my 2 lambda. I have L cubed. 2 cubed is 8. So I got the 3 on the bottom. Okay, so the 2 cancels with that. That makes it a 4. 4 times 3, I have a 12. Okay, now remember, lambda is a linear mass density. Lambda is mass per length. So right here I have lambda. I'm putting in the mass of the stick divided by the length of the stick. Okay, so one of the L's go away, and I wind up with 1/12 ml squared. Okay, now we need to know this, okay, because this is a basic shape of nature that rotates, okay? A stick about its center of mass, right? You could think about maybe a bicycle spoke, okay? Maybe think of that as one going across, okay? Or maybe like a ceiling fan, all right? So you could either treat it as one way you could treat it as a stick, okay? Kind of ignoring the center, rotating about the center. Right? So that's a common shape of nature, a stick that rotates, okay, about its center of mass. All right. Now, so the thing is remember when we did moment inertia for a point particle, it has the form mr squared. So it's a mass times a length squared, mass times a length squared. So there's always going to be an m, and there's going to be a length squared. Well, what length is associated with a stick? L, the length of the stick. So it has the form ml squared. The 12th just comes out of the integration. Okay, so you just need to know that. Okay, next one is we're going to find the moment inertia of the same stick about the end. So this would be like if that was your pencil and you put your finger here, okay, and you're trying to rotate the stick like that. Okay, rotating about that axis. Okay, so kind of like you're swinging like a baseball bat. Okay, swinging a bat, holding it from the end. Okay, so I want to find the moment inertia about the end for the same stick, all right? Now, is it going to be bigger or smaller than the one we just did? Well, we did the moment inertia about the center of mass, okay? And again, remember, moment inertia has this form, okay? Just think about it for point particles, easier than think about it in terms of an integral, okay? What's the farthest that any mass is from the one we just did? Okay, L over 2. Here, we're doing it about the end, okay? Well, half of the stick, okay, well, half of the mass of the stick is farther than L over 2. So when I do this sum for the one we're going to do now, 50% of the stick is farther than L over 2. So that sum's going to be bigger. So it should have a bigger moment of inertia, and it should offer more resistance to rotate. Okay, so that's why if it's a baseball bat, that's why instead of holding the baseball bat here, some people put their hand here, they choke up on the bat, and that way there's less mass far away from the axis to swing around. It's easier to get around on the bat. Okay. Okay, so I need to do this integration. Okay, so I'm integrating x squared dm. X is the distance out to the mass element dm. Doing the same thing. I introduce a linear mass density. Okay, and I have to because the variable of integration is m. And I don't have an m, I have an x. So I have to change the variable of integration. Okay, or change the variable of integration or change the integrand. Here we're changing the variable of integration. We're going to get rid of that dm. So linear mass density is mass per unit length. So m is lambda x. Take a differential of both sides, like when you did U substitutions back in calc class, right? Remember you did u is x squared, and du was 2x dx, same thing. Okay, so here's my dm. I put in lambda dx. I'm integrating now over the length of the stick. I'm going from 0, that's my axis, so x equals 0, from 0 to L. Okay, so lambda comes outside, integrating x squared from 0 to L. That makes life easy because I only have the upper limit. All right, and then where I have my lambda, I'm putting in the mass of the stick divided by the length of the stick. X squared integrates to x cubed over 3. My lower limit, 0. So here's my mass per length. And then I get x cubed at the upper limit, L cubed over 3. So one of the L's cancel, and I wind up with 1/3 ml squared. Okay, so remember the form of moment of inertia. It's easier to think of it for point particles. It's always mass times some distance squared. Mass times some distance squared. Well, there's your mass. What distance or length is associated with a stick? The length of the stick. So it's got ml squared. Okay, ml squared. Just like the last one had ml squared. Okay, the third just comes from the integration. Okay, so we have to know that. Okay, so that's like I said, that's a common object. Okay, here looking down on a ceiling fan now it makes more sense. Okay, so here's a stick rotating. Okay, almost about the end. Okay, on a bicycle, there's your spoke. Okay, rotating about the end. So that's a common shape of nature we need to know. Okay, now let me compare the two. This is the first one we did. Okay, rotating your pencil about the center of mass. Okay, and like doing the rubber pencil here, right? Rotating about almost the center of mass. Here it is the center of mass, versus holding it here and trying to rotate the whole thing. Okay, so that was a 1/12 and that was a 1/3. So if you can remember, one's a 1/12 and one's a 1/3. Okay, and you should always remember the ml squared, right? That comes from this business. It's the mass times the distance squared, right? So that's on the equation sheet. Right, that's on the equation sheet. So if you see it on the equation sheet, you know m times the distance squared, m times the distance squared, it's ml squared. So you got to remember the 1/3 and the 1/12. Okay, or just derive it by integrating. But remember the 1/3 and the 1/12. Which one goes with which? Well, the 1/3, that number is bigger than a 1/12. Right, 1/3 of a dollar is bigger than the 1/12 of a dollar. That's a bigger number. Well, bigger means bigger moment of inertia. Well, which one's harder to rotate? That one is, because you have so much mass further out from the axis of rotation. Okay, so the 1/3 always goes with that one, and the 1/12 always goes with the easy one. And even during an exam, you can grab your pencil from here versus grab your pencil from here. Okay, rotate them back and forth. That one's easy to rotate, that one's harder to rotate, so you know, ooh, the 1/3, the bigger number, goes with that one. Okay, and if I took I end over I center of mass, I took my 1/3 ml squared divided by my 1/12 ml squared, I get 4. That's where this came from. Okay, so this, so this one, okay, moment inertia about the end, okay, if I solve that for I end, is 4 times the moment inertia about the center of mass. So it offers 4 times resistance rotated about the end than it does about the center of mass. And again, that's why people will hold the baseball bat there. They choke up on the bat to reduce the moment of inertia. Okay. Okay, some other ones we need to know, all right, is moment inertia about a hoop or a thin ring. Okay, thin means, okay, that the thickness of the hoop, okay, is thin compared to the is small compared to the radius. Okay, so if you had a roll of tape, okay, that's the radius. All right, the thickness of the tape is not thin compared to the radius. But at the end, when you're done with all the tape, now you just have that thin ring, and that is thin compared to the radius, or that's small compared to the radius. That's what's meant by a hoop or a thin ring. Okay, so I need to integrate that. So I want to find the moment inertia of a hoop. Okay, it could be like a bicycle tire, ignoring the spokes. Okay, or like a hula hoop. Okay, so moment inertia of a ring about its center of mass. So I'm integrating r squared dm. So here's my dm, a little chunk of dm. R is the distance out to the mass element dm. Okay, in r, here r is constant. Okay, it's the radius of the hoop. So when I integrate r squared dm, r is constant, it comes outside. and I'm integrating dm, and dm from calculus class integrates to m. So the moment inertia of a hoop about its center of mass is mr squared, okay? And if you think about it, remember our I is sum of mr squared. Well, that's all messed up. Remember, I is the sum of mr squared, okay? For a hoop, okay, all the mass is as far away from the axis of rotation as can be. So there's the thin hoop, there's the axis of rotation, all the mass is as far away as you can get, so that coefficient is big. What's the biggest it can be? Is 1, okay? I know a stick looks different, but we had a third and we had a 12th. Here, all the mass is as far away as you can get. It's at the radius, so that's why that coefficient is a 1, okay? That one we need to know, okay? And that one's easy to derive, all right? The other one we can do, and I'm gonna do it on the next page, is for a disk, okay? Moment inertia of a disk, okay? Has the same form. Oh, and then the other thing I keep forgetting is, remember, moment inertia has this form. So mass times the distance squared, mass times the distance squared, okay? Well, there's your mass. Okay, whoops, there's your mass, okay? So what distance or length, okay, what distance or length is associated with something round? The radius, so mr squared. Same thing here for a disk. Has the same form, mass times a length squared, mass times a length squared. So there's the mass of the disk. What length is associated with something round? The radius, so mr squared. Where's the half come from? The half just comes from an integral. So I want to look at that now. Okay, so I want to find the moment inertia of this disk. Okay, that's a disk. Okay, like a penny, about its center of mass. Okay, rotating around like that. Okay, all right. So that's our starting point, except to integrate r squared dm. Okay, but the difference here is, all right, my dm. Okay, so here's my disk, and my differential element of mass is a thin ring. So this little thin ring, okay, is at a distance r, okay? So r is the radius of, I should say, capital R is the radius of the disk, okay? Little r, okay, is the distance out to my mass element dm, and my mass element is a thin ring. So let me get rid of that, okay? So here I have a little thin ring, and I'm going to integrate it all the way out to the end. So here's a snapshot of it when it's somewhere on the disk, okay? So r is the distance out to the mass element dm, all right? So I need to integrate that mass element, okay? So I'm integrating r squared dm. So what I do is I introduce, instead of a linear mass density to change the variable of integration, I introduce an area density, because this is a two-dimensional object. It's like a flat penny, okay? So this is the letter sigma. That's a small sigma, okay? That's a big sigma. This is a small sigma. So most books use sigma for area density, mass per unit area. So sigma is mass per area, m per a. Solve this for m, okay? Take a differential of both sides. Okay, take a differential of both sides of that. So dm is sigma dA. Right, what is my dA? Okay, that's the differential chunk of area, okay, for my mass element. Well, here's that mass element. It's a thin ring, okay? Well, what's the area of that ring? So I took this red ring, that differential area, all right, and I stretched it out and laid it on the table, okay? So what's the length of that mass element? Okay, it's 2 pi r. Right, there's my, and again, this is for an infinitesimally thin, okay, strip. Okay, so if this is infinitesimally thin, okay, then the distance around is 2 pi r. Okay, and this thickness, okay, so the thickness of the ring, okay, thickness of that ring is a differential element dr. So my picture, r is a distance out to my mass element, dr, okay, there's my dr, that's the thickness of the ring. So the area looks like a box, length times the height. So there's a length times the height. So that's my differential element of area dA. So here I have dA, I'm putting in 2 pi r dr. Okay, so I'm integrating r squared dm, so that's my dm. Okay, my 2 pi comes out. Okay, my sigma, that's my area density, that comes out because that's constant. All right, and I'm integrating what I have left. I have r times r squared. So I'm integrating r cubed over the disk. So the variable r goes from 0 out to the edge, right? Disk has radius capital R. Okay, well, I can do that. I'm just integrating r cubed. All right, so that stuff's outside. This integrates to r to the 4th over 4. But sigma, that sigma is mass per area. So it's the mass of the disk divided by the area of the disk. So for sigma, I put in mass per area. So my pi's go away. The 2 cancels out part of the 4. That exponent cancels part of that one. And I'm left with 1/2 mr squared. Okay. So again, if you think of moment inertia for point particle, easiest way to remember it, okay, it always has a mass times the length squared, mass times the length squared. Well, there's my m. What length is associated with something round? The radius, okay, and the half just comes from the integration, all right? Okay, so that's where that came from. Go back, okay? That was for a disk. Okay, now for a cylinder, all right? So let's say I have a penny, and let's say I have a stack of pennies. Okay, this is a stack of pennies of some height h. Okay, well, this is definitely, stack of pennies is a cylinder. Okay, well, what is 1 penny? Is 1 penny a cylinder or is it a disc? Okay, well, the penny's on the ground, you're looking at it, looks like a disc. Okay, but if you're a little flea, see that one right there? If you're a flea that was on the back of another flea, that disc looks like an enormous cylinder. Looks huge. So the good thing is, it doesn't matter whether you call that, it doesn't matter whether you call a penny a disc or a cylinder. Okay, it's the same. Now here's the weird thing. The moment inertia for about the center of mass, okay, about the same axis, for a solid cylinder has the exact same form. It's 1/2 mr squared. So you look at that and you say, oh, well, if I look at the difference between 1 penny and a roll of pennies, okay, the difference, if I look at it, well, what about that h? Why doesn't that the height show up? Okay, because it's definitely, okay, definitely should attribute something to it. Well, the h shows up right there in the m. Okay, so if I have 1 penny, that's going to be 1 penny. I have the mass of a penny. Here, if I have a stack of pennies, now I'm going to have a larger mass. So this letter h, oops, that letter h, okay, is in is a height that's parallel to the axis of rotation. Okay, it's along that direction, and only things that go outward from the axis of rotation attribute to the moment inertia. So the h isn't being ignored, it actually shows up in the mass. The more height you have, the bigger mass you would have. Okay, so it doesn't matter whether you call that thing a disc or a cylinder. Okay, probably better to call it a disc and call that a solid cylinder. Okay, so that's another shape. The shape we need to know besides the 2 sticks and the ring is a disc. Okay, another common shape of nature that rotates is a solid sphere. Okay, and its moment inertia has the same form: a mass times the length squared. Mass times the length squared. What length is associated with something round? The radius, so mr squared. The 2/5 just comes out of the integration. So I think if you click on files and look on lecture notes, okay, on the Wiley site, okay, I have this, the moment inertia of a solid sphere. Okay. Okay. Don't worry about this. All right. So this is just a big mess. All right. So here, the differential element of mass here was a thin ring. Here, it's a thin disk. Okay. So you integrate this, it's just a big hairy mess. Okay. And at the end, out pops a 2/5. Okay. So there's your m length squared, your mr squared. Okay. And the 2/5 just comes from the integration. Okay. So that one we need to know. Okay, I'm never going to ask you for this, so don't worry about this page. Okay, I just want to show you that's where the 2/5 comes from. Okay, and later we'll see that had something to do with the rolling ball lab that we did. All right, so whoops. Okay. So what I did is I think I took this picture from our book. Okay. So out of this table, these are the ones we need to know. We need to know the moment inertia of the thin ring. Okay. About that, I'm sorry, moment inertia of this thin ring about that center of mass. Not necessarily this one. I'm not asking you to know this one. Okay. Don't worry about that, because this is a totally different geometry. Okay. Here, all the mass is as far away as you can get. Here, that's not evenly distributed. Okay. So that's totally different. Okay. So you need to know that one, thin ring. So a hoop. Where's the disc? Hoop. Disc. Okay. And it doesn't matter if you call it a cylinder or a disc. So a disc about that axis. Okay. About that axis passing through the center of mass. Okay. This is also a disc or a cylinder, and the axis does go through the center mass, but it's a different orientation. So that's totally different. Okay. But if you notice, if I have, if this radius gets really small, this radius shrinks, that term goes to 0, and you're left with that. And that's one of the ones we do know. So that's a stick about the center of mass. That we did. Okay. Then we need to know the stick about the end. That was this, but with a third. Okay, stick about the end. So hoop, disc, sphere, and those two sticks. Okay, so don't worry about that. Okay, don't worry about that. Don't worry about that. Don't worry about that. Okay, don't worry about that. Okay, so I got one disc and cylinder, and then the two sticks. Okay, I want to look at another example of moment of inertia. Okay, so this is the example we did. We had two masses far from the axis of rotation, two masses close in. I told you that you could build one of these in front of you with a ruler or a yardstick or a pencil, okay, with an eraser attached, all right? So we saw that the top one was difficult to rotate, bottom one was easier to rotate, okay? Both of these objects had the same mass, but the top one had a lot of its mass far from the axis of rotation, which gave it a large resistance to rotate, so it had a large moment of inertia. The bottom object had the masses close to the axis of rotation. Okay, so it had a smaller moment of inertia. It was easier to rotate. Okay, so we have to look and ask, what's in it for us? Okay, so how can someone use this? So actually there's a whole industry that was developed just out of this concept of minimizing a moment of inertia. Okay, so let's say you take a backpack, and the manufacturer, they put the pockets for the water out here, all right? So here's some backpacks. This is at Philmont in New Mexico, okay? So there's a water bottle, okay? There's another one, all right? Okay, so what people realize is, well, the difficulty with having the water bottles on the outside of the pack is it looks more like this picture. Okay, so you have your heavy items out here. And the problem with that is, if let's say you're standing somewhere, okay, if you're walking around or climbing, that if you have your heavy objects on the outer side, okay, then you have a large moment of inertia, which means not only does it offer a large resistance to rotate, but if you walk and step and your body's rotating and you want to stop, okay, then you also have a large resistance to stop rotating. So your body stops rotating, but all the heavy stuff in the pack wants to keep rotating. It's going to take you with it. So you want to take the heavy stuff, the heavy water bottles, not put them on the outside. You want to put them closer to the axis of rotation. Okay, so you want to move them closer in, but you also need access to water. So how can you have both? You can still have all your heavy water, but you want to put it close to the axis of rotation to minimize the moment of inertia. Okay, so the idea is you want to lower your resistance to stop rotating. Okay, and the solution to that is, okay, whole industry was built on the concept of these water bladders. All right, so what you do is you take all that heavy water that used to be on the outside, and you put it close to the axis of rotation. So it goes in the back of your pack. Okay, so it's still in the pack, but it's close to your back. So it's close to that axis of rotation. So it more looks like that rather than that. Okay. So the smaller mass objects, okay, like for example, your sleeping pad or something that doesn't weigh a lot, that goes on the outside. Okay, that can go far from the axis of rotation. The larger mass items, the heavier items like your water, you want to put that inside close to the axis of rotation to make the moment of inertia smaller. Okay, so what the Camelback does, okay, instead of putting the water bottles far from the outside or far from the axis of rotation on the outside, you put them along your back. So if this is, there's you, there's your body. So the Camelback is almost pressed along your back. So now you've minimized your moment of inertia. Okay. So again, you're not changing the mass. Okay. You've taken that water and you've just moved it. So you're not changing the mass. You're just changing how the mass is distributed with respect to the axis of rotation.